Welcome, grade 12s, to day 28, period 4 of Coronachem. Today is Wednesday, May the 13th of 2020. And we're starting a new chapter. It's called Chemical Kinetics, and it is chapter 14 of your textbook. Let's begin with an analysis of what affects reaction rates. There are four major factors that affect the rates of reaction. They are the physical state of the reactants. So for example, finely powdered reactants dissolve and react more quickly. If you tried to dissolve a tablespoon of icing sugar, you would find it a lot easier than trying to dissolve granulated sugar. And you would find it easier to dissolve granulated sugar than to dissolve a similarly a crystal of similar mass, because it's a question of surface area. When you have something finely granulated or finely powdered, you increase the surface area of the solid, and it allows more interaction with the solvent, so it will dissolve more quickly. They'll have the same, all three will have the same ultimate solubility. They'll saturate the solution the same way. They'll reach their maximum at different rates, however. The maximum solubility will be reached more quickly with the finely granulated sugar. In gunpowders, they do that too. Rounds that are adapted for shorter barreled rifles tend to have a finer granulation so that they burn more completely and achieve maximum pressure to propel the bullet sooner. Because if you have a 357 2-inch barrel Magnum, you only have 2 inches for that bullet to accelerate. So all the burning has to take place largely inside of that time period in which the bullet is traveling down the barrel. If you have a longer barreled gun, you can afford to allow the powder to burn a little longer, so they tend to granulate it slightly differently. The different loads are adapted for the different split-second conditions that occur during the chemical reaction. In explosives technology, they talk about brisance. It is the breaking power of an explosive. It is related to, in part, how finely granulated the formulation is. There are obviously other factors. Some explosives can be made to have a much higher detonation capability. And also, it's a question of how the explosives work. Some explosives have a very high rate of reaction. They break down very rapidly. And their propagation is something like 8 kilometers per second. But in the old-fashioned explosives, it was more of a deflagration, meaning the stuff would burn really quickly. And the way to increase the power output of the explosive was to confine it, granulate it more finely, and then of course to compress it. So when you compress an explosive, it quickly builds up pressure, and by building up pressure and temperature, you increase the rapidity of the reaction and the violence of the explosion. Which brings me to the other three factors. Concentration. If you increase the concentration, you also increase the frequency of productive collisions. Because there's more molecules in proximity to each other, they're more likely to interact, so you tend to increase the rate of the reaction when you have an increased concentration of the reactants that participate in the reaction. Also, increasing the temperature. Clearly, temperature is a direct measure of the molecular motion of atoms. The higher the temperature, the more the atoms are jiggling and vibrating, and have the higher kinetic energy they have. So when they collide, they're going to have a higher energy collision, which tends to be more conducive to reaction. And lastly, you have catalysis. Catalysis means you introduce a substance or an enzyme or something that will help the chemical reaction to take place more quickly. The thing itself, the catalyst itself, remains unchanged at the end. It tends to be regenerated at the end of the reaction. By definition, a catalyst is something that's regenerated by the end of the reaction. So for example, in your body, essentially every chemical reaction that happens in your body has a specific protein attached to it called an enzyme, which helps to catalyze, which helps to speed up the reaction so that it can happen within a reasonable time frame. For example, the act of breathing in air causes the exchange of oxygen and carbon dioxide at the surface, at the membrane surface of the alveolus, where that's where the blood gases are exchanged. So you breathe in oxygen and you release carbon dioxide. There's a special enzyme in your lungs that helps to catalyze the conversion of bicarbonate, which is in your bloodstream in liquid form, in aqueous form, dissolved in the liquids of your blood, and it helps to catalyze the conversion of the bicarbonate into carbon dioxide and water, and helps so that your body releases carbon dioxide at your lung surface. That's how you get rid of your carbon dioxide. There's an enzyme called carbonic anhydrase. If you didn't have that enzyme, you would not be able to exchange gases, and you would quickly die. There are certain situations where you actually want to slow down the efficacy of that enzyme. There's a substance, I think it's called Diamox, which is given to people who are suffering from altitude sickness. And what it does is it inhibits carbonic anhydrase so that you don't exchange too much CO2 out of your blood, because when you're at high altitude, your breathing rate increases dramatically and you tend to blow out too much carbon dioxide, and you go into something called metabolic alkalosis, which throws the pH of your body down. It starts to raise your pH. So because you can't slow down your breathing at high altitude because you need the oxygen, what they do is they give you this medication that slows down the efficacy of the catalysis at your lung membrane surface so that you don't lose your carbon dioxide as quickly, and you can continue breathing rapidly without getting altitude sickness, because altitude sickness can kill you in a matter of 24 hours if it's serious enough. You literally start getting fluid on the lungs, you start coughing, you can't stop coughing, and you get high blood pressure in your brain and other issues. And by the time you start coughing up pink foam, you're in big trouble, and you got to get down to sea level, or you can die within a few hours. Okay, so those are the four things that it can affect the rate of a chemical reaction. Now let's look at how we analyze the data that is produced during chemical reactions in the sense of the rate. The average rate of a reaction is equal to a negative delta A concentration over delta T. Oh, by the way, this is all chapter 14. A negative sign is used because it's showing the disappearance of a reactant. If you were looking at the appearance of product, then you could use a positive number. The rate is an average because in chemical reactions, the rates vary. With all of the factors listed before. So, as the reaction is proceeding, it's using up the reactants. So that tends to lower the concentration of the reactants. And as you lower the concentration of the reactants, you tend to slow down the reaction. Also, in some chemical reactions, in biochemical reactions, for instance, sometimes you even have the products of the reactant. The products of the reaction can actually plug into the enzyme that is making the reaction go faster, and they change the shape of the enzyme so the enzyme slows down. That's called feedback inhibition. So your body has all kinds of mechanisms like that to slow down the enzyme once you get enough of whatever your body needs. It can sometimes even throw the enzyme into reverse, or it can deactivate one enzyme and reactivate another enzyme so that the chemical reaction going the other way is catalyzed. So the body has all kinds of control mechanisms. You want to talk about a system that has all the trappings of artificial intelligence. You look at the human body. Human body is like just a big computerized system with all the algorithms interacting appropriately so that you continue living. And if one of the algorithms fails to work, you get disease. And if you're born with one of these problems, then you get what's called an inborn error of metabolism. Very often it can cause you to die early in life, or if the inborn error of metabolism is big enough, it kills you even before you're born. That's where most miscarriages happen. Most miscarriages occur because the baby has an inborn error of metabolism that is incompatible with life. And sometimes the mother's blood circulating through the baby's body can mask the weakness of the baby, but as soon as the baby becomes more autonomous, the defect kills him. And that's what causes most miscarriages. On page 578, practice example, it asks, for the reaction pictured in figure 14.3, calculate the average rate of the appearance of B over the time interval from 0 to 40 seconds. Figure 14.3. Okay, so in figure 14.3, I guess I should show it to you. I mean, you have the textbooks, but just in case you forgot your textbooks or you don't have them handy, this is figure 14.3. Maybe take a screenshot. It's not focusing. Okay, so it shows a reaction proceeding, and it's a concentration of chlorobutane, it looks like. No, it's not chlorobutane, it's just A. They call it A. A is turning into B. The red balls are turning into blue balls. Okay, so I'm going to do it using that formula. So negative delta A over delta T. Enter all the values. So at the beginning of the reaction, you have a concentration of 1 mole. And at the end, you have 0.3. So the difference is 0.7 moles, the beginning minus the end. And the time lapse is 40 seconds. So it starts at 0 seconds, ends at 40 seconds. The difference is 40 seconds. So you get 0.7 over 40 seconds. 0.7 moles over 40 seconds. So basically, the reaction is proceeding at the rate of 1.75 mole per second. And you're only allowed 2 sig figs, so it ends up being, the book writes 1.8 mole per second, rounded up. This is an average rate. It makes no mention of the fact that the reaction might, you know, if you were to graph the reaction coordinate, or the reaction, the appearance of product, or say the disappearance of reactant, you would see something like that, or you might even see something like this. You have no way of knowing. It's most likely to be going to be shaped like that. It's going to have a curve. It'll happen quickly at first, and then it'll start slowing down as the reactants start to diminish in concentration. It's unlikely that you will get a shape like that unless it's a catalyzed reaction where the enzyme is what you call saturated. On practice example on page 580, they ask you to determine what's called an instantaneous rate. And instantaneous rates are the brainchild of Isaac Newton. That's why he invented calculus, so he could determine instantaneous rates. When you have a curve that looks like this, depending on where you measure the rate, you're going to get different amounts of rates. If you measured here, you could draw a tangent to the reaction, and change in y over change in x, it gives you the slope. m is equal to delta y or delta over delta x. But if you took that same tangent, a different tangent over here, that's more like a secant, but anyway, you would see that it changes the slope dramatically, and the reaction has dramatically slowed down later on. So you can take instantaneous rates by taking a tangent of a curve and expressing that as a rate. And that's what the calculus, that's the power of the calculus, because it helps you determine these instantaneous rates on a reaction where the rate is ever changing. On practice example 580, I think they have just another example of, no, they're asking you to do an instantaneous rate. So what you do is you draw a tangent to the curve at that point. So using figure 14.4, now it's based on this, this picture here from the text. I'll show you. They're using this. So you have to draw a tangent to the curve, basically draw a straight line that touches the curve at the point of interest, and then you drop a perpendicular and you make a triangle out of it like they do here, and they did another triangle over there. And that way you can determine the slope. Delta y over delta x gives you the slope, and that gives you the instantaneous rate at that point where it touches the curve. I did it in my notebook, and I'll show you what I got. So practice example, page 580. And you have the change in the chlorobutane concentration over time. This means change, that delta symbol, that little triangle. So it starts off at 0.09. Mind you, I eyeballed all this, right? So you might get slightly different numbers. It's not the end of the world if you get slightly different numbers than me or the book, because it's inherently inaccurate. And if you want to have an accurate calculation, make the graph bigger, use a ruler, don't do it freehand, it'll look like a dog's breakfast, and you'll get answers that are way off. So 1.15 times 10 to the negative 4, molarity per second. So you're only allowed 2 sig figs, so it comes out to around 1.2 times 10 to the negative 4. Okay, this is what students love to do. They write down the exact answer that they get in the book. What that tells me is you either don't understand what you're doing, or you're trying to make it too perfect. Don't try to make it too perfect. You're doing it for yourself, okay? So get the wrong answer. If you're off by 10%, I don't care. It's an exercise for you. So do it the right way, which is you'll have, it'll introduce some slight errors. When you put down exactly the same answer as the book has, all that tells me is you're just copying what the book answer is, but you're not probably learning anything. End result of that's going to be that you're going to put a slightly different number. Sorry for being cynical, but just do it, okay? On page 580, give it some thought. Figure 14.4 shows two triangles that are used to determine the slope of the curve at two different times. How do you determine how large a triangle to draw when determining the slope of a curve at a particular point? Well, a good rule of thumb is the bigger you make it, the more likely it is that you'll have an answer that's going to be believable and closer to the truth, right? So use a ruler, draw your things carefully, plot your graphs carefully, and use the full page if you can. You get better results that way. I wrote, give it some thought, page 580. Bigger triangles allow for a more accurate representation of the curve's slope at that point. It is easier to visualize if the lines are longer. You know, if you have a bigger thing to look at, then you can see the details of it more easily. You can read the numbers off on the graph more easily, and so on. There is a stoichiometry in rates. I'm not going to write you the equation, though it's in the book. You can see it. The stoichiometry is the same as the stoichiometry you would do for any other calculation. So basically, bottom line is, if you have 2 moles of reactant turning into 4 moles of product, then the disappearance of the reactant will be half the rate of the appearance of product. I'll show you what that looks like. On practice example, page 582, needless to say, you should read the book. If you don't read the book, all this is going to sound like Greek to you. And if you're Greek, it'll sound like Chinese. Okay, so we have a typical reaction here. Dinitrogen pentoxide turning into nitrogen dioxide and oxygen. 2 moles of the dinitrogen pentoxide yields 4 moles of nitrogen dioxide. So in the first part of the question, it asks on page 582, if the rate of decomposition of dinitrogen pentoxide at a particular instant in a reaction vessel is 4.2 times 10 to the minus 7 molarities per second, what is the rate of appearance of nitrogen dioxide and oxygen? So the rate of appearance of nitrogen dioxide is going to be twice the rate of disappearance of dinitrogen pentoxide. So you start off with a 4.2 times 10 to the negative 7 molarities per second times 4 moles of nitrogen dioxide appearing for every 2 moles of dinitrogen pentoxide disappearing. Moles cancel, and you're left with 2 over 1. So the answer ends up being 8.4 times 10 to the negative 7 molarities per second. For part B, they say what is the appearance rate of oxygen. So now that it's 2 moles of this disappearing gives you 1 mole of that appearing. So 4.2 times 10 to the negative 7, again, molarities per second, times 1 mole of O2 appearing for every 2 moles of N2O5 disappearing, gives you an answer of 2.1. Because you're basically taking that number divided by 2. You get 2.1 times 10 to the negative 7 molarities per second. On section 14.3, they talk about the rate law. Rate laws tend to have exponents if some of the reactants have a greater effect than the others with respect to concentration. So in some reactions, when you double the concentration of one of the reactants, you end up quadrupling the rate of the reaction. So the effect of that particular reactant would be squared. Okay, and you can also have non-integer values, but let's not complicate it. In the book here, they keep it pretty simple. They say, 1 or first order, second order. Some reactions are 0 order, meaning that no matter what the concentration of the reactant, it doesn't speed up the reaction. This happens, for example, when you drink alcohol. Your liver is an organ that detoxifies alcohol, right? So it's a certain size sitting there in the left side of your rib cage. No, it's on the right side, upper right quadrant. Sorry, your liver's on the right side. So your liver's sitting there on the right side. It's a certain volume, a certain size. It has a certain amount of enzymes. So you drink alcohol. The alcohol goes circulating through your blood, and then when it hits your liver, it gets picked up by the enzymes that catalyze the hydrogen, the oxidation of the alcohol to acetaldehyde, and it turns into I forget what in the end. But anyway, it detoxifies the alcohol. But once you've filled up the liver's capacity, it can't go any faster. Okay, so that age-old myth, if you have somebody who's drunk, just give them some coffee and then they'll sober up. No, what you get is an awake drunk. Your body will metabolize alcohol at a specific rate. Once it's saturated, once you've filled up all the sites where the enzymes are there to help detoxify the alcohol, then it's going to chug along at the same rate for however long the alcohol lasts. So if you drink a lot, you might end up being drunk for hours until your liver can detoxify all the alcohol. Okay, and that's a 0 order reaction. It proceeds at a rate that is directly related to the size of your liver and how many enzymes you have, and obviously how much alcohol is circulating in your system. So there's 0 order, first order, you can have even second order. It's even possible to have third order, I suppose, where if you double the concentration of the reactant, you will make the reaction go 8 times faster, because 2 to the power of 3 is 2 times 2 times 2, or 8. We'll do some example. How does that look like mathematically? Thought you'd never ask. So this is section 14.3 of your text. Rate equals rate constant times the concentration of a product A raised to the power of m
times, a reactant A raised to the power m times a reactant B raised to the power n, where K is equal to the rate constant. The rate constant doesn't change. It is fixed.
Unless you change the temperature. If you change the temperature, then you change the value of K. But you assume that when you do your experiments, you're controlling the temperature. You don't want your temperature going all over the place because temperatures affect the rates of reaction. M and N are usually, underline usually, small whole number. They're usually small whole numbers, leave it at that. And A and B are concentrations of reactants. So a rate law, on give it some thought, on page 581, it asks you, I don't know where I got 581, there is none. It's 583. It says, what is a rate law? Yeah. And B, what is the name of the quantity K in any rate law? Okay, a rate law predicts the production of products or disappearance of reactants on the basis of experimental results. The results from one set of conditions may be used to predict results from another. Very often they use what are called initial rates. Remember how I told you that a reaction will tend to slow down as it progresses because you're starting to use up the reactant. So what chemists do is they'll measure the reaction rates at the very beginning of the reaction by drawing tangents on the decrease of the substrate. And that way they can extrapolate and find out what the rates are at the very beginning, where the concentrations are a certain amount. And then from that, they can establish a rate law for other concentrations. You could do multiple experiments at different concentrations to help corroborate your results and then develop an average. Some reactions happen so quickly that you can't do them, you can't collect the data using regular, just by observation and writing down. You just wouldn't be able to do it fast enough. Some reactions, I remember when I was doing experiments for my master's thesis, some of the reactions I ran lasted less than 1 second. I would have to use a special machine called a stopped flow spectrophotometer, meaning they inject with 2 syringes the 2 reactants into a chamber, it swirls and mixes, and then the machine measures the increase of color change, and the reaction would collect 100 data points in about 1 second. So there's no way you could do that, humanly speaking. Some of the other reactions tend to be very slow, and sometimes they were so slow I would start the reaction and go and buy a coffee downstairs, come back, and it was just finishing. So that you collect data, and then you could run, you can analyze the data using various mathematical approaches, which we will talk about later. So on page 585, practice example, they show you how this works out. So they give you a set of data, and then you're supposed to derive the rate law for that. Practice example 585. It's actually page 584. I don't know what maybe I did it on a different textbook. I don't know. Anyway, it says, assuming the rate is equal to K times A. Okay, it says it's 585, but it started on page 584. Assuming the rate equals K times A times B, rank the mixtures represented in this sample exercise, the one that starts on page 584, bottom of the page, in order of increasing rate. So they have a series of red and blue spheres in a box, and you're supposed to rate the rate of reaction on the basis of the concentration of the different spheres. You see that? It looks like that. Okay? You read through it. This is a chapter I recommend you read through carefully. Don't skim it, because you're going to miss on key concepts, and you're going to find it mystifying. So practice example, page 585. How much time we got here? Oh my gosh, we're going fast. Page 585. So this will be the last example, and then I'll
give you just a little bit of homework. So if A concentration is equal to red spheres, I'm going to erase all this on the side. It's interfering. And B is equal to the, look like purple to me, purple spheres. So box, and if the rate law is equal to K times concentration of A times concentration of B, both to the power of 1, then your rate in the various boxes, there's 3 different boxes. In box 1, you're gonna get rate is equal to K times 5 red spheres and 5 purple spheres. So your rate is going to be 25K. Do we really care what this number K is? No, because it's the same constant all the way through. So we're just interested in the algebraic value of it, not the actual number. Box 2, the rate is going to be equal to K times 7 red spheres and 3 purple spheres, so you're going to get a total rate of 21K. And in box 3, you get a rate equals K times 3 red spheres and 7 purple spheres, so you also get 21K. So if you rank them according to rate, 2 is equal to 3, and they're both less than 1. So to find the units of the rate constant, rearrange the rate law to solve for K. You can do that. Remember to write the units correctly for each quantity, or else you're obviously going to get the wrong units. So I'm going to stop it there for today, but I'd like you to try practice example 2 on page 585 tonight. Just do that one practice example. So your homework is this. Homework, practice example, page 585. Where is it? Yeah, number 2, the second one. Also, why don't you watch something from the playlist? There is a playlist called Kinetics. I know every time I tell you this, it must be like saying something like, give me your molars. But I do have a playlist that you can watch where you learn all about kinetics. So feel free to watch that too. But more importantly, read the textbook. All right, I'll see you tomorrow.